Bismillah ar-Rahman ar-Rahim. So these are some of the examples I selected to demonstrate some of the problems we can have in chapter 3. First, these are some of the concept questions. Of course, I ask you, to solve all the concept questions that you can. Let's go through a few of them. First, it's asked, is ice water a pure substance and why? Well, we know that the chemical composition is H2O for both the ice water and the liquid water and the water vapor for that matter. So iced water is definitely a pure substance. Then what is the difference between saturated vapor and saturated vapor? Well, there's no difference. I bet I meant liquid. Saturated liquid, of course, is a liquid that is about to boil or just undergoing or starting the boiling process, so transition between the liquid state and the vapor state, and saturated vapor, that is liquid that is, vapor that is just about to condense, go back from, return from the vapor state to the liquid. Some of it will have started to condense if any heat, additional heat is taken from it. Then, why are the temperature and pressure dependent properties in the saturated mixture region? There are more than one way to answer this problem, but the short answer is that any heat addition will be like you'll be adding like latent heat. So they are dependent because it boils at a certain temperature and certain pressure, and any heat you add will not change the temperature, the phase change temperature, provided that the pressure stays the same. And then, is it true that water boils at high temperature at higher pressures? Well, we know that at higher pressures, more of the force is being applied at the surface, at the free surface of the liquid water. So you need more force, more interaction, more internal energy, more kinetic energy for the molecules in order to break free these intermolecular bonds. So it will definitely boil at higher temperatures, at higher pressures. In fact, this is the idea behind the pressure cookers that we discussed in class. Also, if you remember the TSAT and PSAT, they go something like this. So the higher the saturation pressure, the higher the temperature pressure, and vice versa. Next, it says, is it possible to have water vapor at -10? Well, yeah, it's possible if you reduce it. We missed that. Is there a difference between a critical point and a triple point? Of course, by definition, critical point where there's no difference between saturated vapor and saturated liquid states, so it becomes kind of a plasma. And the triple point is at the other end of the saturation dome, where the three phases of a substance can coexist in equilibrium. Of course, below the triple point, temperature below, for example, 0.01 degrees Celsius for water, for example, you can't have three phases or two phases exist in equilibrium. And this is tied to the next question: to have water vapor at -10. Of course, you can. Then a household is cooking beef stew for this family in a pan that is uncovered, covered with light lid, and covered with heavy lid. This is tied to the pressure. Okay, so what will be shortest? Of course, with the heavier lid, because it applies a higher pressure. In what kind of pot will a given volume of water boil at a higher temperature? A tall, narrow one, or a short, wide one? Pot, you have a pot and you have a heated pot, water, a given volume of water higher temperature and tall and narrow pot, or a wide and short pot. Well, there are a number of variables here. Is the same heat transfer applied here and here? I mean, the same heat flux at the surface, at the bottom surface, or not? Of course, this seems to boil faster because this has a higher area, but assuming in the temp Q is the same, they should boil at exactly the same amount of time. Of course, if you consider the heat transfer out of this pot through the walls, for example, is it full? And هذا كله wall, this all water, and this is at a higher temperature, so heat will dissipate here, so you will lose more heat. This will be, if this is full, for example, you will not lose heat. You will also lose heat from the surface. So it's a bit tricky question. So let's leave this aside. So does the amount of heat absorbed at 1 kilogram saturated liquid water boils at 100 have to be equal to the amount of heat released as 1 kilogram of saturated water vapor condenses? Of course, and this is the definition of SFG, HFG or UFG. Okay, this is we call the latent heat of vaporization and latent heat of condensation and all that. What is the physical significance of UHFG? Can be obtained from knowledge. Of course, this is just the difference, takes it from saturated liquid to saturated vapor. So this is Hg minus Hf. Okay. This, does it change with pressure? I think I gave you this in a quiz somewhere. Of course, yeah. If you remember if you remember the saturation dome, this is H, this is T and H. This guy is the HFG, and you see that it becomes shorter and shorter as temperature increase, right? Which probably quite, yeah. So as pressure increases, this gets shorter. Which process requires more energy, completely vaporizing 1 kilogram fresh liquid water, wet atmosphere, or completely vaporizing 1 kilogram at 8 atmosphere pressure? Well, we just said that at higher temperature this is shorter, so that answers this question. Under what condition is the ideal gas assumption suitable for real gases? We said when they are away from the saturation dome. So at high temperature and low pressures, and or low pressures. So the pressure is low and the temperatures are, or the temperature is high. What is the difference between R, specific gas constant, and universal gas constant? They are related. One is just the kilojoules per kilogram Kelvin, and one is kilojoules per kilomole Kelvin. And you just multiply this, divide this by the molecular weight, which is kilomole, and use kilograms. So you multiply this by m, and you'll get a specific gas constant. Propane, methane, commonly used in heating in winter, and the leakage of these fuels, even in short periods, poses a fire danger for homes, of course. Methane اللي يطلعون like power plants with refineries. Propane is what you use for your gas stove at home. So let's say they pose a fire danger. Which gas leakage do you think poses a greater risk for the fire? Greater risk for fire. Okay, again, it depends on many things. Open area, closed area, but basically, I think what they're after is the molecular weight. Methane is lighter than propane, so propane is heavier than air. So if you get a leak, it will settle. It will settle at the bottom of the room. Whereas methane will just it's more volatile. It will float and hopefully dissipate and cease to be a danger for fire. What is the principle of corresponding states? We didn't focus on this a lot, but in terms of the compressibility factor, it says that at the same reduced pressure and temperature, they all have the same compressibility factor, Z. Okay, so Z is the same for at the same TR and PR. So the corresponding states. We didn't focus on it, but you should. Well, I think the book talks about it, but we didn't mention it specifically in class. But it's just an idea. The same reduced pressure and temperature, they all have the same Z. How are the reduced pressure and reduced temperature defined? Just the pressure divided by the critical pressure and the critical temperature. So that's that. A common question is to do the table. So if you have a table handy, as I do here, you'll see. You'll see, and the first thing you should do, of course, is check the pressure. So this is refrigerant. So you go to table A12, right? The pressure table for the saturated refrigerant 134, and you look at line 600 kilopascal, and you see the corresponding Tsat, or actually you don't have Tsat, you have HF and HG, and in the middle, of course, HFG. So you'll see this guy, is it lower than HF or higher than FG? These two values at 600 are, give me 1 second, these are 81 and 81 point something, 0.5, and this is 262. So this looks like a saturated mixture, right? This is 180 between them. X is just HF plus X times HFG. So you have this from the table, you have this, and you have this 180. And the temperature is the saturation temperature, 21.5. So this is 21.5. Same thing, this is easy, saturated mixture. This is between 0 and 1, so saturated mixture. And you have and a saturated mixture. So this guy is, you go to the temperature table, and at -10, you read off the saturation pressure. I'll tell you what it is. So this is 200.7, around 200, and HF, I mean H, the actual H is just HF plus X, HFG, same thing, اللي هو يطلع whatever. Again, you go to the temperature table. هذا شكله معطينا 2, so probably superheated, but let's check. If you check superheated, let's go to table 11, A11, and at 14, at -14, the pressure, so at -14, P sat is 170. So if it's 170, then and this is higher than 170, so this must be, this must be compressed liquid. And it's higher pressure. It boils at 170, but then I increased the pressure, so I quashed any activity, any molecular activity, and it went from the saturated state or saturated mixture or saturated liquid back to the compressed liquid, And this, I could use the HF, around the HF, and this is undefined, and this is the compressed liquid. Finally, when the temperature is 44 and the quality is 1, this is easy, saturated vapor, and I'll read off the table. I'll tell you what this is. 44, so Tsat is 1130 kilopascal, and H is just Hg, whatever that is. Okay, and now the saturated vapor, and so on. So when you do this in an exam, it's a good idea to show your work, show your rationale. So for example, when you say this at 44, at T equals 44, Tsat مثلا, Psat equals هالكثر, so it's saturated mixture, and saturated mixture H is equal to. So give me a line or two explaining your thought process. Okay. So let's look at another question where you have like a first law, not a first law. It's just a first law plus some properties lookup. I hope to have different, split them between parts that ask you for the properties, and parts that ask you for application of the first law of thermodynamics. But oftentimes you will have problems where you have to look up properties in order to solve the problem. So let's read it together. A piston-cylinder device contains piston-cylinder device. So it's a good idea to draw a schematic. Have a piston-cylinder device contains. Say M is equal to 0.85, and this looks like a closed system, so this is M1 is equal to M2 of refrigerant 134A. Okay, at T1 is equal to M1 bad minus 10 degrees Celsius. I'll look at the state. The piston is free to move and has a mass of, the mass of the piston is 12 kilograms. So it looks like I will add up maybe atmospheric pressure and the mass of the piston in order to solve for the pressure inside. But let's wait. So 12 kilogram, diameter of 25, so D is 25 centimeter. Okay, or 0.25 meters. So I'll know that it's a circular, so piston. So I know the area, right? Well, the area of the piston is pi over 4 d squared. This is pi over 4 0.25 squared كمتر اللي هو عندي. So the local atmospheric pressure is 88, so P atmospheric, write it here, P atmospheric is 88 kilopascal. طبعا if I want to do the thing with the piston and the piston area, I need to apply a force on atmospheric here, anticipating. Now heat is transferred to the refrigerant, so there is some Q in, until the temperature is, so M2, and in a closed system, let's be complete, until the temperature T2 is equal to 15 degrees Celsius. And we want to determine the T2, the final, and P2, the final, nothing T2, and the change in the volume of the cylinder. Okay, so B, I want V2 أو delta V اللي هي V2 minus V1, the change in the volume. ما عندي لا V ولا V2 ولا V1 أقدر أطلعها. And lastly, the change in the enthalpy. So the change in the enthalpy of the refrigerant. Okay. So I need three things. What do I have available? I have properties, lots of properties. I could complete أشوف إذا عندي like other information. But it looks like I need to do a summation of forces. I need to a summation of forces. عندي pressures هني وعندي pressures هني مع mg وعندي pressure جاي من هني. So summation of forces هذه واحدة in the y direction. And عندي first law وعندي وبس. I think this is all I have. So let's try to fix the first state. So the first state, I have the mass and I have the temperature, and I don't have the pressure. So how would I get the pressure? If I do summation of forces, I'm going this is the pressure from the refrigerant, and this is the pressure from the piston, and this is the atmospheric pressure. And if I multiply this by the area of the piston, and by the area of the piston, and by the area of the piston, I will have, well, I will just, I don't need to multiply by this. So the pressure, the pressure P2 is equal to P1. So the pressure is equal to the summation of the mass of the piston, the weight of the mass of the piston times the area, and the atmospheric pressure, the atmospheric pressure contribution. So this is on one side, right, 4 is equal to minus minus. So on the right hand side, what's going down is P atmospheric plus P the pressure اللي هو force, right? Force times divided by, so F اللي هو mg on piston divided by the area. So I have this as P atmospheric اللي هو 88 plus mg كم هذا 12 kilogram 9.81 meter per second square divided by the area اللي هي pi over 4.25 square. هذا راح يعطيني شنو؟ يعطيني كيلو باسكال and this راح يعطيني باسكال. So I need to divide it by 1000. Okay, never forget this. لأن هذيل الام جي وربعهم كله يعطون باسكال. So I have P2. So P1 عفوا عندي و P2 is equal to P1 لأن هذا ماكو لا spring وراء فوقه ولا شيء. So this is P1 is equal to P2. From the first state, so طلعنا P2 is equal to P1 عرفنا. And then the change in the specific volume أقدر أطلع V1 من هني. So what is V1? طلعها من التيبل. عندي properties. إيه عندي ال specific عندي temperature and the pressure. So I can get the initial specific volume and نفس الشيء بالنسبة للفاينل specific volume. I could look it up in a table. So V1 معروف من التيبل و V2 معروف من التيبل معناته أطرحهم من بعض and I'll use the mass. I want volume, not the specific volume, difference in volume. So هذا V1M هذا V2M M minus M V1. So هذا هو delta V كبيرة. Okay, so I'm done with this, but then I need the change in enthalpy. And in enthalpy, I need to apply the first law of thermodynamics. So I guess I need to determine أيضا in addition to V H1 or H2 من the table. So it's easy to look them up. So most of the activities here related to looking up numbers from the table. So ماكو work interaction ولا nothing. Then I have no this is Qn minus Q out ماكو plus work in ماكو minus work out في work out في work out ولكن في boundary work out بدال delta U I'll say in delta H I'll remove this guy. So this is M H2 minus H1. Okay, so I have M or H to H, so I'll get the QN. And then that's it. Yeah. Okay. So this is the change in enthalpy. Yeah. Actually, change in enthalpy. Never said anything about the Q, but change of enthalpy is due to the Q. So, yeah, and if you want to answer this, no one asked about the Q. They changed about delta H. Okay. Another problem has to do with water now, not refrigerant. So we have 1 kilogram of water at 2 megapascal. And it's contained in a 150 liter of rigid container. Rigid container, there's no boundary work, no boundaries because this is rigid, so I'll be using internal energy throughout. So let's draw it, مثلا, and this is the pressure. P1 is equal to 2 megapascal, and mass ما راح تغير. This is 1 kilogram. Nice round number. And the volume this is 150 liter. I know 1000 liter is 1 meter cubed, so this is 0.15 meter cubed from the get-go. The water is cooled, so there is a Q out to a final temperature of T2 40 degrees Celsius. I have no information about T1 yet. We want to determine the initial temperature. So T1 is unknown, and the final pressure. So P2 is unknown in the container, and you want to show the process on a PV diagram. Well, the process on a PV diagram, I don't know what about the pressure, but I know it's a rigid container. So for PV, whatever this is V, this will be a straight line. And the volume is constant. V1 is equal to V2. So it just changes where this vertical line happens in terms of saturation dome. So let's work on the properties because I have P1 that is 2 megapascal, and I have V1 which is nothing but V1 V ما تغير or V ماكو V1, it's just V, M which is 0.15 divided by 1, so this is 0.15 meter cubed per kilogram, and I can look up my table A5 just to determine the thing. I have a table A5 with me in front of me, and I'll look at table A5, and it says at 2000 kilopascal, the saturation temperature is 212 degrees Celsius. So at 2 megapascal, pressure of 2 megapascal, Tsat is 212 degrees Celsius. And then بس أنا أبي شنو؟ أبي specific volume, and then specific volume شنو ال VF is 0.00 0.00117 Rad, and Vg is 0.099587. 0.099587, and this is 0.15 معناتها the specific volume greater than the specific volume of a saturated vapor. معناتها grew from the saturated liquids or mixtures or vapor and then continued on increasing in size. So this started out as so phase or state 1, phase 1 was a superheated vapor. Okay, so I'll go to my A6 table and I'll look at the 2 megapascal subtable, and I'll see in the أشوف هذا at 0.15 and it tells me in the 0.15 the temperature is just below 400. I'll do some interpolation. So, but when the specific volume is 0.15122, the temperature is 400. So this is less than 400. Let's say this is 390. Okay, 395, 398, 399. So, so let's say in a T at 1 is around 398, well, whatever. Okay, just below 100. So just below 400, and the 400 هو اللاين اللي موجود. Okay, so what do I with the 400 شو أسوي؟ أنا أبي هذا done. I need the pressure at the second state. What do I know about the second state? For one, the specific volume did not change. I do whatever, no mass has escaped, and no boundaries were moved, so the same volume. And for the second state, I'll look at final temperature of 40. I'll go again for my table A4. 40 degrees Celsius. 40 degrees Celsius, table A4, and the specific volume. So at 40 degrees Celsius, I have Psat. إذا كان هذا saturated mixture ما أدري شنو هذا، بس Psat is equal to 75 degrees Celsius. بس أنا ما أبي Psat، أبي I don't care الحين أبي Vf and Vg. بشوف this specific volume between them ولا لا. So Vf at this guy at 40 degrees Celsius, this is 0.001026 meter cube per kilogram. Vg is 3.9933 meter cube per kilogram. You see, in 0.15 is between them. So this is saturated mixture. So saturated mixture, and you want the pressure, or the pressure is the saturation pressure at this temperature, because my specific volume told me, it never changed, told me that this is between these two at this temperature, and I know that this is the final temperature. So that means saturated mixture, and this is my pressure. And if they had asked me to determine the internal energy method, I would have to get the quality first. So Vf plus X Vfg. نحسب لنا BFG, and then I use the quality to determine internal energy ولا enthalpy ولا whatever. So this is how you get pressure and then any other data that you want. Okay, I hope this is clear. Next, we'll look at a question where you have again a piston cylinder device. So water initially at 300 kilopascal. So عندنا piston cylinder device and like T1 is equal to 250 and P1 is equal to 300 kilopascal. Okay, it's a good idea to get these cleanly at the beginning. Contain piston device and fitted with stops. So it's fitted with stops at the bottom or at the top. It's not clear. يعني ممكن stops يكون هني and expand until it hits, ولا stops here and contracts until it hits. Okay, so far we don't know. Allowed to cool. Okay, so allowed to cool معناته راح ينزل. So probably it stops here until it exists in a saturated vapor and the piston rests on the stop. So إذا هذا initial temperature, initial pressure P2 لأنه same pressure, so P2 is equal to P1 and this is saturated vapor at state 2. Okay, so temperature also cool طبعا راح ينزل ما أدري شنو temperature ولكن the pressure remained constant until it became saturated vapor. So this state is fixed. Then the water continues to cool until the pressure is 100 kilopascal. معناته when it صار كذي it continued to cool. هم طلع منه هذا Q. Okay. هم طلع منه Q ولكن هني pressure remains constant, هني volume remained constant. عدل. So it continued to cool until the pressure is نحط state 3, so P3 is equal to 100 kilopascal. On a TV diagram, a sketch with respect to saturation TV. Okay, diagram set with respect to saturation line. شكله آخر جزء اللي من 2 ل 3 straight line لأنه يبي TV وهذا saturation هني وصل هني وبدأ يمشي هني. So let's worry about this later. بس من الحين ندري إن من 2 إلى 3 this is horizontal لأن هذا isothermal لأنه isobaric. This is constant volume, so this is vertical. عدل وصل هني وقاعد ينزل. عدل. Initially this is TV, so these are the isobars. Initially كان constant pressure, so along this line. So بدأ من هني same pressure until it reached this and then same volume. So this is vertical and this is one of these isobars. Okay, this is 1, this is 2 and this is 3. ما أدري وين 3 هني somewhere. Okay, يمكن quality ما أدري شنو صار. And the final state label T, P and V for the second state. We also find the overall change in internal energy. So نبي internal energy. So delta U between the initial and final states. Okay, per unit mass. So per unit mass delta U. And then not delta the Q. So بما أن هذا saturated, superheated vapor, I can get من table whatever table with 300 Kelvin. Let's do this. This is water. So table A6 table A6 جدول sub table مال 300 and it tells me in for the 300 for 250 the specific volume is 0.79645. Specific volume is 0.79645 meter cube per kilogram, and U1 بما أن احنا نبي U1 this is 2728.9, so 2728.9 kilojoules per kilogram. So I have this. What happened من هني؟ هذا fixed. عدل عندي pressure وعندي saturated يعني the quality is equal to 1. So U2 is equal to UG at كم؟ at 300 kilopascal. So that's easy. اللي هو كم؟ at 300 kilopascal. I'll go to table A5. Okay, لأن عندي the pressure. So I'll go to table A5 أو table A6 هم يعني. أول واحد saturation pressure. So at 300 temperature is 133. I don't care about temperature. أبي internal energy UG which is 2543.2. So this is U2 is 43.2, and the specific volume اللي هو UVG. So V2 is equal, لأن هذا اللي راح يبقى عندي من V3 is equal to V2 ما راح يتغير. So V2 اللي هو VG at 300 kilopascal اللي هو VG 0.6582. Okay, 0.6582 meter cubed per kilogram. So هذا هو نفسه هذا. So 100 kilopascal, again I want to fix this state and the pressure, specific volume, intensive, independent. So I'll go to table A5 هذه حالتي من table إلى table. So A5 at 100 kilopascal. أشوف إن at 100 kilopascal specific volume for the what this goes between the point O هذا saturated. So VF at 100 is equal to 0.001043 meter cube per kilogram, and VG is 0.41941 meter cube per kilogram. Okay, شو أسوي بهذا؟ I need the change in internal energy from 3 minus 1. So عندي 1 وعندي 2 بس ما ابي 2 ابي 3. So من هذه راح اطلع الكواليتي at state 3 اللي هو راح تصير U minus UFG U minus UFG divided by UG. So by definition, U minus UF divided by UFG. So عندي الكواليتي واقدر اطلع منها U3 is equal to UF plus X UFG. So يطلع عندي هذا كله من التيبل 100 تيبل A5 مثلا، وبذلك اكون طلعت U3 minus U1 أو U1 minus U3 whichever you want. So it says in the change internal energy, change internal energy, you could give it as minus and it lost some energy, or you could just give absolute من U1 إلى U3, U1 minus U3. One last problem, which is like a tank, air, ideal gas. So a 1 meter cube tank containing air at 25. This is 25 degrees Celsius and 500 kilopascal. So and then a pressure or temperature P1 or T1. And in a V1, 1 meter cubed, it's connected through a valve to another tank containing 5 kilograms. So here notice in the ما أعطاني الماس وهني ما أعطاني الvolume. So this is 5 kilogram. So this is M2. Okay, يعني 2 التانك يعني وهذا 2 التانك 1 التانك at 35 degrees Celsius and at 200 kilopascal. So this is fixed and أقدر أطلع from ideal gas هذا reasonable. So PV is equal to RT. So I have عندي الماس والR of air is 0.287 and the temperature. So I have everything I need هنا. عدل الفوليوم عفوا احتاج الفوليوم. So I'll say نكتبها بالطريقة الكبيرة. نقول P1 V1 is equal to M1 RT1. Okay. من الفيرست تانك بطلع الماس اللي هني. So M1 is equal to P1 V1 over RT1. So this is عندي P و T و V وعندي M1. أيضا حق التانك الثاني شنو اللي ناقصني؟ عندي الM وعندي T وعندي P. I need V. Okay, so V2 is equal to M2 RT2 divided by P2. أيضا عندي هذا mass, temperature and pressure. So عندي everything I need. Okay. Now the valve is opened and the entire system is allowed to reach thermal equilibrium with the surrounding at 20 degrees Celsius. So this is open. صار شيء واحد. I know when they opened, let's call it state 3. اللي هو الماسز نفس الشيء. So mass صاروا نفس الشيء. So M1 plus M2. So عندي الماس. الR طبعا عندي. I'll say this is 1, this is 2, system 2, will 3, and the M3 is equal to M1 plus M2. So this is عندي والR عندي. How about the temperature? Temperature هني صار في heat Q in and out, I don't know. ولكن الفاينل equilibrium هذا اللي يبي من environment and it reached the final equilibrium at 20 degrees Celsius. So T3 is 20 degrees Celsius. Notice that here we'll use Kelvin, huh? This is Kelvin. Kelvin. Okay. ولكن معطيني إياها 20 degrees Celsius. So what do I have? Any other information? Yes, I do. لأن connected صاروا كلهم مع بعض. Valve is opened and usually الvalve hopefully إن هذا الvalve والpipes هذيل مشمولين من الانيشال فوليوم. So هذا الفوليوم includes هذه وهني الفوليوم includes هذه. الvalve شوية راح وزادوا شوية 1 بالمليون من الفوليوم بس إنه doesn't matter. So V3 is equal to V1 plus V2 أيضا عندي. So temperature final volume, final temperature, final volume. R عندي so شنو يبي؟ Determine volume of the second tank. Well, عندي the volume of the second tank. I already did. And the final equilibrium pressure هم هذا. This is M3 اللي هو مجموعهم R T3 اللي هو قال لي إنه في equilibrium minus V over V3 اللي هو مجموعهم. So this is V1 plus V2 and that's that. These calculations are not that complicated, ولكن you need to pay attention to how you define your system. شنو 1 or شنو 2. It's not the state 1, state 2 of the same mass. ولكن this is a problem and this is a problem, and we combine them to give states. So I hope that's clear. Okay, lastly, صدق عاد هالمرة. You have a rigid tank, again volume constant, whose volume is unknown, is divided into two parts by a partition. So this is interesting. So we have a partition here and volume is unknown. One side of the tank contains an ideal gas at 927. 927 عشان when you add 273 يصير شيء round number, شيء زين. So let's see راح يصير كم 273 مع هذا راح يصير 1200 Kelvin. Okay, nice round number. So ideal gas هني, so this is T1 at 1200 Kelvin. من الحين حطه عشان ننسى. So 1200 Kelvin. The other side is evacuated. So this is vacuum. Okay, this is vacuum, and this is important. You see, vacuum. You know that we studied in the boundary work that the boundary work is the work done by the compressed gas against the environment. هذا الwork, the pressure اللي أعلى من atmospheric pressure, so this is work قاعد يقاسي and it's pushing this out. هني there is no boundary work and this is evacuated. بس أنا أشيل partition and it will expand يروح without any force. Without any force, nothing, no atmospheric pressure to combat this force. So they can freely expand. So that's the difference between like an expansion of a gas in a piston-cylinder device and the expansion of a compressed gas into the evacuated part of the tank. Okay, I believe I have an example in the book actually. And has a volume twice the size of the part containing the gas. So V1 I don't know, ولكن V2 is 2 times V1. معناته بالنهاية I know إن V3 is equal to 3 V1. لأن 2 من هني و 1 من هني, so 3 أضعاف. So anyway, the partition is now removed and the gas expands to fill the entire tank. So I know إن whatever mass عندي هني هو اللي الماس 3. So mass 3 is equal to M1. بس إنه it's too heavy. Heat is now supplied or applied to the gas until the pressure equals the initial pressure. So pressure اللي هني طبعا. So this is P1. Let's say ما ندري شنو P1. This is P1. هني ماكو شيء. P nothing. Okay. So P3 is equal to P1 لأن في heat transfer. Q in out. المهم I don't care. Okay. Until the pressure equals the initial pressure. Determine the final temperature of the gas. So we want T3. If we want T3 في أشياء constant. Hey, في أشياء can we say definitely that في أشياء yes الماس M1 M3 is equal to M2. الM ما تغير. So I could cut M out of any ideal gas equation of state. عدل. And the ideal gas has state 1 and state ماكو state 2 قلنا ماكو شيء 2, so this is P3 is equal to P1. شنو ال P3 وال P1? I can say in ideal gas M1 is equal to M3 again. So شنو ال M عبارة عن PV divided by RT. So P1 V1 over RT1 is equal to P2 V3 over RT3. This is M. So M is constant. M1 is equal to M3 and then ماكو M2. Okay. So R is constant, so the same. And it tells me the heat is transferred until the temperature comes back to until the final pressure equals the initial pressure. So these are the same. And the volume, I know in V3 is equal to 3 V1. So how many unknowns I have? So I have basically 2 unknowns in it. So V1 over T1 is equal to V1 over 3 V1 over T1 T3. So I'll solve for this, and then this will go away as well. So I'll have T3 is equal to 3 T1. We multiply. وقلنا T1 is 1200. So this is 3 times 1200 Kelvin. So this is 3600 Kelvin. So this is my final temperature. You see, there is no complicated math. So you could just maybe solve it in your head. I can't, but maybe some of you can see through the problem in the M تروح والR تروح والR. You could model this in your head, and you could model V, relation between V, and you say, okay, the V إذا هذا by 3 times الأصلي معناته temperature is 3 times الأصلي. That's that. I'll see you.